a high-def 10-year movie of the universe?
You would need 400 ultra high definition TVs in order to display one full image at its full resolution. Up to 10 million alerts per night that we expect from the Rubin Observatory. Maybe there is this other massive planet that could be anywhere from like 10 to 15 times more massive than the Earth.
Are there people calling this planet X?
The NSF DOE Vera C Rubin Observatory is currently under construction in Chile. It will conduct an unprecedented decade-long survey of the optical sky through something called the Legacy Survey of Space and Time, or LSST, which maybe you've heard of when the Rubin Observatory is talked about sometimes. Once Rubin begins operations later this year, it's going to revolutionize the field of astronomy and what we know about the universe.
Is there any of this stuff that's being kept secret, or is all the data you're generating going to be fully accessible to any academic institution that wants to look at it?
Yes. Okay, absolutely. So the really cool thing about the Rubin Observatory is that all of the data that it's going to collect is going to be available to everyone. And so everyone, any scientist at an institution in either the US or in Chile will have immediate access to all of the data that is coming out of the telescope. There will be alerts that will actually be generated immediately after Rubin takes an image. It will then compare that image to older images of the same patch of sky. If it notices that anything has changed between those two images, within 60 seconds, it will send out a worldwide alert to everyone that something changed. This is what it is. This is where it's located. And this is all the information that we have about it. And that's going to be, those alerts will be worldwide public within 60 seconds of the image being taken for every single image and every single object that changes between all of those images. So we expect something like up to 10 million of these alerts on any given night throughout this 10-year-long survey.
That's a lot of data.
It is. It's a lot of data. When we talk about this being an unprecedented data set, it's really unlike anything that we've had available in astronomy before.
So I think you intimated that this sort of survey has not been done before, but I want to ask you, is that true? Not this kind of survey hasn't been done. So this is the unique aspect of what Rubin is doing this comprehensive survey. Is that true?
Yeah, it's partly the survey, but it's largely the observatory itself, the telescope, the way that the design of the optical design of the telescope, how big the mirrors are, and how they're actually put together, which I'm happy to talk a little bit about some more, as well as the camera being the largest digital camera ever made. And
how many megapixels?
Yeah. So let's talk about the camera a little bit. This camera, in physical size, it's roughly the size of a small car. So it's about 5.5 feet across and about 10 feet long. And it weighs 6,600 pounds, so more than 3 tons just for the camera itself. The front lens is about 5 feet across, and it's the largest ever built for this kind of a purpose. So it's this massive, massive camera. Its most important feature is that it has the ability to capture incredible detail over a huge, vast area of the sky in each image. So it has 3,200 megapixels, which is 3.2 billion pixels. So if you want a comparison, the typical camera on your phone has about 12 megapixels. So this...
You said 3,200?
3,200 megapixels compared to 12. So
That's a
it's
big
about
camera. Yeah.
250 times more pixels than your phone's camera. And the resolution is so great that in order to be able to display just one of the camera's images, you would need 400 ultra high definition TVs in order to display one full image at its full resolution.
So I'm sorry. I'm still processing that. So to display uh, one image that this camera takes in full detail, you would need 400 high definition sets.
Yes, TVs. Yes.
That's a pretty big wall of
Yes.
TVs. That's bigger than most man caves.
Most of them.
That would be one huge man cave to have a display that big. Okay.
And so the camera's images, one more cool fact about the resolution is that the resolution for this camera is good enough that it would be able to fully resolve, so very clearly see a golf ball from about 15 miles away, all while covering an area of the sky large enough to include 45 full moons. So it's this incredibly detailed capability over a huge patch of sky in every single image that the camera will take. That is one of the incredibly unique parts of the Rubin Observatory. And it's going to take 1,000 images every single night for 10 years and create this incredible ultra high definition movie, essentially, of the universe.
As it continues operation over multiple decades, it will truly be a movie because you're going to see the universe changing as we go along.
Yes, absolutely.
I wanted to ask you just a little bit more specific, a bit like I'm an amateur photographer, but I know there's a thing called depth of field, and basically you have to choose what's in focus.
Yeah, so I think one of the benefits for taking pictures of things out in space is that they're so far away that you don't have to worry about focusing at different depths like when you're closer because everything is so far away. They all look like point sources essentially until you can take a picture of them that kind of magnifies them a bit and you can actually see all of the details. So we'll be able to see uh, galaxies in quite beautiful detail as well within these images, as well as individual stars and things like that. But they're all so far away, excuse me, that you don't really have to worry about. I mean, you want to make sure that your telescope is very, very finely tuned so that you have the focus good enough that you take these incredibly clear images. But for the most part, the focus is at infinity, essentially.
Infinity. Yeah. I answered my own question. As soon as you started talking, I'm like, of course, it's at infinity. So it's all in focus. Okay. Maybe what I'm getting at is like, I'm going to ask a question that potentially could be stupid, which is like, you have to assume, like, could one galaxy be blocking the view of another galaxy? I mean, like, is that a problem you have to deal with? And if so, how do you get around that?
Yeah. So it is quite possible. And we've actually already observed it many times where there are galaxies that are behind other galaxies that are kind of in the foreground. And so we can't directly see the galaxies in the background because the one in the foreground is blocking it. But sometimes when that galaxy that's in the foreground is massive enough, it can actually bend the light that's coming from the galaxy in the background around that galaxy in the front. So this is called gravitational lensing. And you can then see as that massive galaxy is bending the light from the galaxy in the background, you can kind of see these arcs of light, kind of the galaxy the light from the background galaxy being kind of smeared out in these kind of arc shapes around the edge of the galaxy in the front. And if you get just the right perfect alignment of looking at a galaxy that has another galaxy directly behind it, you can actually get something called an Einstein ring, where you see this complete circle, this ring of light smeared out around the galaxy that was in the front, where that ring of light is the light that's coming from the galaxy in the background that's being bent by the massive
Oh
galaxy.
my God. It's like a halo of another galaxy. That's a halo. So the galaxy in front has a halo of the galaxy behind it.
Yes.
Oh my gosh. Like is because I was just thinking through like most of space, I mean you hear this, most of space is empty. So to get a situation where one galaxy is blocking the view of another galaxy just shows how deep this telescope is seeing actually. Uh, so it's seeing really, really deep because it's mostly empty, and the probability of one galaxy blocking another is you need to be seeing super deep for that even to be a problem.
And so to try to quantify it, the Rubin Observatory is expected to find, I think, the number over its planned initial 10-year survey of the night sky is expected to find something like 20 billion galaxies, most of which we've never seen before over this 10-year time. And so
We're going to find
we're
20
in
billion
far
galaxies,
these galaxies,
new
right?
galaxies. Wow.
Yeah.
All right, let's go zoom back in, which is so the survey that it's doing. Did you have to build a special telescope to do this? And how is the technology, other than, I guess, bigger camera, more megapixel camera, what other things distinguish Rubin from the telescopes that have come before it?
Yeah. So the other thing we can talk about, in addition to the camera, is just the telescope itself and the design of the telescope. So Rubin Observatory includes the 27.5-foot diameter Simone Survey Telescope. And its optical design, so how the mirrors are designed to direct the incoming light into the camera, is unique. It's unlike any other optical design for a telescope in the world or in space.
Mainly because of the scale required. Like basically you're focusing so much light on. You need to focus so much light on to the lens. Is that why?
Right. So you have this very large mirror. There's actually only two pieces of glass that make up three different mirrors. So the largest mirror and the smallest mirror are carved out of the same piece of glass. And the two parts have different curvatures along them so that they reflect the light at different angles. So, in the middle of this 28-foot diameter large piece of glass is what's called the third mirror or the tertiary mirror. And it's kind of makes up a circle in the center. And then outside of that is a ring that is the primary mirror or mirror one. And both of these have slightly different angles to be able to direct the light at different angles. And so the way it works is that you have light that comes in from the sky. It reflects off the outside ring of this 28-foot across mirror. It reflects that up to mirror two, a secondary mirror that's a separate piece of glass that's about 20 feet away from the first one. And then that second mirror reflects the light to the inner part of the big piece of glass that is mirror three, which then reflects the light into the camera. So the light bounces back and forth off of these three mirrors on just two pieces of glass that are about 20 feet apart. So it's a very compact design before it then the light enters the camera and you take your picture of the night sky. So it's this combination of this very large light collecting area with these big mirrors, this compact design that lets the light very quickly go through the optical system and into the camera so that you can take a picture. The very sensitive detectors that you have within the camera itself as well, that allows the telescope to take these very deep pictures over a really large patch of sky and do it very, very quickly as well. So because it's so compact, the whole setup, it's called the telescope mount assembly, that has both of the two mirrors and the camera and all of the electronics and everything. Altogether, this telescope mount assembly weighs about 220 tons. So it's this big steel structure that has the two mirrors and the camera and all of the needed electronics that will all be hooked into it. And so it's this huge, massive thing. But the really cool thing is that despite its weight, the telescope, because it has this compact design, actually can move at an incredibly fast speed. And it's actually the fastest slewing telescope of its size in the world. So each time it takes a picture, which is going to cover a part of the sky that's about the width of 7 full moons across, it'll take a picture. It's then going to,
Hold on. The picture of the sky taking is a swath of sky equivalent to 7 moons next to each other. Is that
yes,
what you're saying?
across in diameter. So over the whole thing, you'd
Uh-huh.
be able to cover 45 full moons within one individual image. So
Wow.
the telescope
Okay. That's
takes
a
this,
big picture.
it's a very big picture. Yeah. So it takes this picture, this big picture of the sky. It then has to slew. So it moves to the next patch of sky that's that same width of 7 full moons across over adjacent to it. And it has to move and then stop and be rock solid still to be able to take another extremely clear picture and then move and settle to the next picture. And it does this in between each image, takes less than 5 seconds. So you have this massive thing that's moving incredibly fast. It's the fastest moving slewing telescope in the world. And in fact, when it's operating at maximum speed, it moves faster than a person would be able to run. So, for obvious safety reasons, nobody is allowed within the telescope dome structure when the telescope is actually moving and operating.
And you said this thing weighs like 200 tons.
Yes.
So
Yes.
this 200-ton thing is moving faster than a human. And the reason you want it to move fast, so you can capture more images. So otherwise, the survey would take 100 years, not 10, right?
Right. Yeah. So, in this way of being able to take these pictures so quickly, the Rubin Observatory can take about 1,000 pictures of the night sky each night. And it's able to then cover the entire visible sky, so the entire southern sky, since it's in the southern hemisphere, every 3 days. And then it goes back and starts again. So every 3 days, it's going to take and it's going to see everything in the sky. And then it's going to do it again 3 days later. And it's going to do it again 3 days later. And it's 10 years. And that is where this incredible ultra wide, ultra high definition movie of the night sky comes from that the Rubin Observatory is going to produce.
Okay. You just clarified a huge misunderstanding I had, which is I thought it would take 10 years to complete the pass one. That's what I thought. Like, because I know when I just read the materials, just very cursory, that's what it seemed like. Oh, it's a 10-year survey of the sky. I'm like, oh, yeah, the sky's pretty big. It might take 10 years to survey it. But you're saying it's surveying it every 3 days so that over 10 years, you're going to have a movie.
Yes.
So it's a 10-year movie of our universe. Wow. Okay. That is That's not what I understood. Like that's even more amazing. Just even a survey of the sky itself is pretty amazing. But now, okay, now I understand. It's a high def movie of the universe, a high def 10-year movie of the universe.
Yeah, yeah, it's pretty incredible. And all of these things combined together, all of these different aspects of how the telescope was designed and this amazing camera are all of the things that make it possible for Rubin to be able to do this and make it completely unique compared to any other telescope that because there are a lot of telescopes that have been surveying the sky and taking pictures, trying to cover the entire sky over time. There have been many telescopes that have done these night sky surveys before, but they don't cover nearly as large of a patch of sky at once, and they don't go nearly as deep. So, seeing things nearly as faint and as far away as the Rubin Observatory can do, and they don't do it in as quick of a cadence of covering the night sky as quickly as the Rubin Observatory. So it's very unique in that way. And because it will see so far away, such faint things over the entire sky, it's going to create this huge amount of data, these up to 10 million alerts of things changing in the night sky and discovering 20 billion galaxies and all kinds of just incredible things. My brain doesn't even really know how to quite wrap itself around how much data and information about the universe we live in is coming very soon because of what this observatory is going to do.
So why Chile, of all places, to put this thing? And also, where in Chile?
So it's on a mountaintop in Chile called Cerro Pachón, and it's in the northern-ish region within Chile. And there are two adjacent mountaintops in Chile. There's Cerro Pachón and Cerro Tololo that already have a number of telescopes on them. And so Rubin Observatory is getting kind of added to one of these really great locations. And the reason that there's so many telescopes already up there, and it's a great place on the top of a mountain to be able to have a telescope, is that the higher you can go above the ground, the less atmosphere you have to look through in order to be able to observe things out in space. So you have less interference from the atmosphere with, I mean, all of the turbulence and the air moving around in the atmosphere. It can cause a lot of funny things in your images where it can make it difficult to have a really clear image. And so we have to have things called adaptive or active optics systems that help kind of keep every little part of the mirrors angled at just the right amount to make sure that the light that's coming in is staying focused and is trying to account for a lot of that turbulence and atmosphere that we have to actually look through. So having these telescopes on these mountaintops really help a lot with being able to take clearer pictures of the night sky.
What are the questions we hope to answer? What are the top 5 questions? And then move into the conversation about interstellar objects.
So close to home here on Earth, we, of course, have the solar system, which has the Earth and the sun and planets and asteroids and comets and all of that kind of stuff, which, despite everything in our solar system being pretty close to us, poses challenges because the only thing in our solar system that actually gives off its own light is the sun itself. So everything else we can only see by the light that's actually reflected off of it. So there's actually a huge part of what we believe is in the solar system that we haven't actually seen. And we've only discovered a small fraction of the stuff in our own solar system. So we currently know of about 1 million asteroids and comets in the solar system, which has taken us about the last 200 years to be able to discover using our telescopes. The exciting thing about the Rubin Observatory is that it's expected to find another 5 million asteroids and comets during this 10-year survey. So we're going to go from 1 million, that's taken us 200 years to find, to 5 million more in 10 years. And so that's an incredible amount of discovery in a really short amount of time that's going to help us better understand how the solar system formed, how it has changed over time, all of that kind of stuff. So solar system science with these asteroids is what I do. So I'm more than happy to talk about that in more detail. But one of these 4 key science goals for the Rubin Observatory is to create this much better census of all of the objects in our solar system, because there's so much of the solar system, especially in the outer solar system, that still remains unexplored because we just can't see those small things that are far away. And so that's one of these 4 key science goals.
When you say this, our solar system, does it kind of stop at Pluto, or does it go further out than Pluto to be? And technically, that's still our solar system.
Yeah, the solar system is actually much larger than just out to Pluto. So beyond Pluto, and even in the region where Pluto lives, is a disk of asteroids and comets called the Kuiper belt that is much like the main asteroid belt that sits closer in to the sun between Mars and Jupiter. There's this second massive, even more massive flat disk of millions of objects out in the outer solar system. Some of them are even as big as Pluto is itself. And so that extends out. So Pluto is about 40 times farther from us than the sun is. The disk of these asteroids and comets out near Pluto extends out to up to 100 times the distance between us and the sun, or even farther. And then,
So basically, Pluto, from a solar system perspective, we're only kind of halfway through the solar system at Pluto. There's another half of the solar system that exists beyond Pluto, and basically these are just things that are kind of trapped in the sun's orbit, and that's kind of all the things that are in the sun, trapped in the sun's orbit, is technically part of our solar system. Is that how I should understand it?
right, yeah, everything that orbits around the sun that is trapped here by the gravitational pull of the sun is part of our solar system.
So interesting. Like as a child, you learn about Pluto and you think of it, that's the edge.
Right,
But
right,
you're like, nah, we're just halfway through, you know?
right. But that's not even actually the edge beyond that. So there's another part of our solar system. So the planets and most of the asteroids, even out in this Kuiper belt beyond Pluto, all kind of fall, for the most part, in a pretty flat disk. So around the sun, that is pretty flat and doesn't extend. It's not like a big circle or anything. It's just kind of this big flat.
Why is it flat
disk.
versus, I would think, spherical? Like why is it flat versus like being evenly distributed like in a spherical shape?
So it's because of how these planetary systems can form. So as you have originally systems like our solar system, when our sun was just forming, start as a cloud of a bunch of gas and dust that then starts to kind of gravitationally collapse on itself. And as it does that, it can also it spins, it rotates. And so as all of this material is kind of moving around and collapsing in order to conserve angular momentum, so it's a physics problem, as all of this material is starting to move around, it ends up collapsing into this kind of flat disk type of structure. And this is something that we see in young planetary systems as well, things that are stars that are still forming that kind of have these clouds of gas and dust around them as they're starting to kind of collapse into these disk structures. So it has to do with how these planetary systems form and how these stars form as well. But the other cool thing about the solar system is that even beyond this kind of, we don't even actually know where the edge of this disk might be. If there is an edge, or if there's not an edge, or if it extends out even farther than we can currently see. But beyond that, there's something called the Oort cloud. Maybe you've heard of Oort cloud comets before. And this is actually a sphere of comets that are still gravitationally trapped by the sun. So they still orbit the sun, but it's this massive cloud that is anywhere from 1,000 times farther from us than the sun is, out to 10,000 or maybe even 100,000 times farther than the sun is away from the Earth. It's this huge sphere, the spherical shell, basically, of comets that are also still part of our solar system, but they're very, very far away from us. And the reason that we know that this Oort cloud exists is because it's possible for stars to pass close enough to the outer part of this cloud, this Oort cloud of comets, and actually pull enough on the orbit of one of these objects, to pull with its gravity, that it can change the orbit of the comet, which moves its... So how do I explain this? So instead of being on this big circular type of orbit very far from the sun, it can stretch the orbit out, which also means that the closest point along its orbit, so the closest distance that it comes to the sun, actually decreases. So part of its orbit is now much, much closer to the sun than it originally was. And we see these comets, these Oort cloud comets, actually pass through the inner solar system on these incredibly long orbital periods. So how long it takes them to go around the sun one time. So we have found many of these Oort cloud comets as they get kind of yanked on by a passing star, which changes their orbits and makes them pass through the inner part of the solar system where we can see. And they're these beautiful comets that have these bright comas and these long dust tails as they're passing close to the sun for often the first time is when we see them. And so we know that there has to be this giant cloud of these comets that are also in the outer solar system that kind of form this spherical shell around the disk where all of the, like what we normally think of as the solar system, with all of the planets and the asteroids and stuff, sit like that as well.
And we see these Oort cloud comets because they pass near the sun. Is that how it's basically, and we're working backwards. We saw them first and then work backwards into this is the kind of trying to figure out, okay, that was strange. Where did that come from? And then that's how this hypothesis of like, well, there's an Oort cloud and there's many of these out there, and they're kind of located in a spherical location around the sun.
Right? Yeah.
Okay, interesting. Okay, so you stepped us through one of the missions, which is to look at kind of our own solar system and get a greater understanding of what's in our own solar system. So what are 2, 3, 4, like maybe more quickly, a little bit more quickly? So I want to get into the interstellar objects.
Yeah, definitely. So one of the other goals, science goals for the Rubin Observatory, is to be able to kind of better understand the structure of the Milky Way galaxy itself. So the galaxy that our solar system sits in. And so by being able to map as many of the stars as we can within the Milky Way.
How many stars are there in the Milky Way?
So I don't know how many stars are in the Milky Way, but I do know that it's expected that the Rubin Observatory should find roughly 17 billion stars in our galaxy.
So
And
like the
so,
sun, like our sun,
like
so
our sun,
there's 17 billion of those.
right? At least
At
there will be
least
some
in
that we
the
won't
in
be
this
able to
thing
see.
called the Milky Way. Okay,
Right,
so
right.
all
And so
right.
we want to find all of these stars and be able to kind of map the structure of the Milky Way, being able to better understand how the Milky Way formed and kind of how it's changed over time, whether there's evidence or how much evidence there is for whether it was smaller in the past. Often galaxies form by smaller galaxies colliding together and forming bigger galaxies. And so we can see evidence of this, of streams of stars that kind of come off of the Milky Way in these like little twinkling octopus arm type structures. And so we want to be able to map all of these stars that we can within the Milky Way to be able to better understand how the Milky Way itself formed and has changed over time. So that's one of the other science goals for the Rubin Observatory.
Okay. So kind of going outwards, so from the stepping out from the solar system now, the galaxy of which we're a part, just one out of 17, at least 17 billion stars.
Right. Yeah. And so then if we take another step beyond that, beyond the Milky Way galaxy, I talked a little bit about these up to 10 million alerts per night that we expect from the Rubin Observatory of things in the night sky that have changed, even potentially over relatively short periods of time. Sometime this could be things that are in our solar system, asteroids or something that just move across the images, but it could also be things like a star exploded. So a new supernova is discovered because suddenly you have a star that got much, much brighter than it was. So finding as many of these, they're called transients, as possible is kind of the third of the four science goals for the Rubin Observatory.
Okay. Interesting. And number 4?
Trying to better understand the nature of dark matter and dark energy. So, how these galaxies are kind of clumped together in the largest structure across the universe in this cosmic web of these long, kind of lengthy, stretched out filaments that are clumped together, that are clumped in a way that is forced by dark matter being a part of actually the largest part of the matter within the universe. And then also trying to better understand dark energy as well and how it's causing the universe to accelerate as it's getting bigger.
The fact that the galaxies are distributed in their particular way, is it a hypothesis that it's dark matter that is causing this? Or is it acknowledged it's dark matter that's causing it, and we need to figure out what the nature of the dark matter is?
So I think it's a little bit of a combination of both. We can actually see this kind of clumpiness for these galaxies. We can see on these very big scales that there is this kind of filamentary structure with the galaxies that we can currently see. And with how much mass we can see in the matter from those galaxies that's actually emitting light. So all of the stars essentially that are in those galaxies, when we do the math, we know that it's not quite enough mass to be able to gravitationally cause this kind of clumping that we see. There's
Ah,
not really a
okay.
reason that they should be so clumped in this kind of structure. And so the only other thing that we have to try to explain it is this dark matter that has mass as well, that would mean that it has gravity, that would be pulling things together and causing this structure. But there's way more mass that is needed to create this structure that we see than we can actually account for with the visible matter that's actually emitting light that we can see.
Okay, let's shift into interstellar objects. Like we've been building up to this topic. Is this under the first umbrella of looking at objects that are close to us, like in our solar system? Is that where that line of investigation resides? And what is what kinds of things are considered interstellar objects?
Yeah, so finding more of these interstellar objects is definitely part of this goal to be able to increase our census of objects within our own solar system. Finding anything that passes through our solar system kind of falls within that general goal. So these interstellar objects would be part of that because while they're close to us, they're not part of our solar system, but they're close enough that they're on the same scale as the things within the solar system that we're looking for.
And interstellar meaning like it's coming from a different solar system.
Yes. Yeah.
Possibly another galaxy as well.
Right. Yeah. Yeah. So these anything that would be interstellar is something that is considered to not be gravitationally bound to our sun. So it's not actually in orbit around our sun. And it's on a trajectory that can only mean that it came from somewhere outside of our solar system. So from another planetary system around another star, most likely from something within our own galaxy. Other galaxies are pretty far away for something to have come from another galaxy. But as we just said, the Milky Way has tens of billions of stars in it from the huge number of exoplanets that we have found, planets that orbit other stars outside of our solar system, that we think that it's quite possible that every single star has its own planetary system because so many of these stars that we found have planets around them. And so these interstellar objects would be things that came from these other planetary systems.
It's the language you use is very interesting because you said these stars likely have planetary systems, and you said like use. I just assumed they would, but use the word likely because all we can see with our instruments is the stars and not the things that orbit them. Is that why you say use the word likely?
Right. Yeah. Yeah, it's difficult to be able to see planets around other stars because planets don't emit their own light like stars do. And so there are a few different methods that we can use to try to actually detect these planets around other stars. Sometimes if the planet happens to pass directly in front of the star, it can dim temporarily the light that's coming at us from that star. And so we can then see that something big must have passed in front of that star that was pretty close to that star that could only be a planet is one of the simplest ways that we can detect these planets. But we can't actually really directly see them, but we can very much see their effect that they have. And so we know they exist in these other systems.
Yeah, interesting. So the interstellar objects in our solar system, we're going to see. Is it suffice to say we're going to be able to see a lot more of them with Rubin, and one of the interview guests I had in previous episode is Dr. Avi Loeb, and he wrote a paper on this interstellar object that an observatory in Hawaii picked up called Oumuamua. And tell me, just kind of compare and contrast, like that the kind of information we got from that observatory on Oumuamua. Had it been Vera Rubin who saw that object, like, is there a huge difference in information would have been able to get on that object? And yeah, just help me understand like the difference between an existing observatory spotting an interstellar object, how likely it is that they're going to find it, the depth of information they're going to find versus what Vera C. Rubin is capable of.
I think the main thing that the Vera Rubin Observatory is going to do for us is be able to find more of these objects, since it can see things that are fainter and farther away than any other telescope we have available now, many of these interstellar objects, there could be many of them that pass through our solar system that we just can't see because they're too small and too faint for us to actually pick up with our current telescopes that just aren't sensitive enough to be able to see them. And so the Rubin Observatory will be able to have a much better chance of seeing these small, faint things as they pass through the solar system at potentially farther distances away from the sun than the two of these interstellar objects that have been found so far. And so I think with what these other telescopes were able to see compared to the Rubin Observatory, the general information we could get about these objects is probably pretty similar to what we can do with the current telescopes and for things like Oumuamua, but Rubin will be able to find more of them. And the more objects we have, we can then be able to get more general information about these type of objects and understand them as more of a population a little bit better. Another thing that we have as well that we didn't have originally is the James Webb Space Telescope as well. That's this space-based telescope that looks at things in infrared wavelengths, so not visible wavelengths. But being able to have the James Webb Space Telescope that could also be able to look at these things, these interstellar objects as we discover them, we could potentially get a little bit more information in addition to what we can get with the Rubin Observatory than we had before with some of these the original
Interesting.
discoveries.
You mentioned we've only discovered two interstellar objects?
Yes.
Oh, so Oumuamua is one. Maybe you can explain just a quick summary of what Oumuamua is, and then what's the second one?
Yeah, so Oumuamua was discovered in 2017, and it flew through the solar system very quickly. And it took a little while, but we eventually realized that it is actually something that is not orbiting our sun, and is something that actually came from interstellar space. It looks very it looked very much like an asteroid. So there was no evidence of any kind of cometary coma or dust tail or anything like that. And it was also rather oddly shaped. And so it was this very kind of, at first we thought it was this very elongated kind of cigar-like type shape. And then once we got more information, we found out that it's this very flat, wide pancake type of shape. And so that was the first object. There were many things that were rather unusual, a little bit strange about it. And we tried to get as much information as we could about it before it left the solar system again and became too faint for us to see. And then 2 years later, in 2019, there was another interstellar object discovered by an amateur astronomer, and it's named after him. It's called Borisov. Most of these type of objects are named after the person that found them, especially if they look like comets, which this interstellar object did. And so Borisov, this second interstellar object, looked in many ways different than Oumuamua did, because it did actually have this beautiful coma and tail. It very much looked like a comet, which is what we expect probably most of these interstellar objects to look like. These icy worlds that kind of have this activity ignited as they get close to the sun. And so it traveled through the solar system even faster than Oumuamua did, and then left very quickly as well. So we again tried to get as much information as we could about this second object as well. But so far, those are the only two we have discovered.
It just occurred to me the other challenge is that it's a moment because they come into our solar system and then they exit because they're a moving object. So that makes it even more challenging. But I mean, I think this is where the Rubin comes in because the survey is so comprehensive and it's done, you're completing the survey every 3 days. So you're going to get a lot of information on this moving object. So, I mean, so it's if there's another Oumuamua object that the Rubin finds, it sounds like we're going to have more data on it. So to help us really understand uh, uh, more about it, would it be true to say that if another Oumuamua like thing comes to our solar system, we're going to have more information because of Rubin?
Yeah, yeah, I think that's absolutely true. I think part of what you said is being able to have the moment of being able to find these things, but with how rapidly Rubin is going to be covering the sky, it's going to be able to re-observe these objects more frequently at the same kind of level that it is able to do that's beyond what we can find with these other telescopes. So having more information, I think will definitely be true for any of these other objects that we happen to find as they're passing through our solar system. I think a large part of that will come from the Rubin Observatory. Um, I know people all over the world will be pointing all of the telescopes that we have at these things, just like with the first two, of trying to get as much information as we can. Because sometimes we only have a matter of weeks or maybe just a couple of months as it passes through before it's gone again. And we don't always find these things on their way into their closest distance to the sun. Sometimes we find them as they're on their way back out. And so we don't like that's an even shorter window of time to be able to look at them as well.
I've read articles of like, well, if we know something's coming at us early enough, we could send something else out there to take a closer look, take a closer picture. Is there true initiatives around that? And could Rubin be kind of the early warning system of letting us know, hey, look, there's something that's coming close to us that we may want to get our act together to send something else to get a better look at?
Yeah, yeah, absolutely. And that is something that is already part of some of the hopes, I guess, and the plans for what Rubin would be able to do. And so there's actually a mission. I think it's still a concept. I don't know if it has full funding yet, but there's a spacecraft that the European Space Agency has been thinking about building called Comet Interceptor,
No
which
way.
is something.
This sounds like out of science fiction, but the European Space Agency actually has some type of program that's in some stage of development
Yes.
for intercepting comets.
Yes.
Okay.
Yes.
Uh-huh.
And interstellar comets would be probably one of the coolest things for this comet interceptor spacecraft to be able to go take a close look at. So the way that this would work is that, as you said, the Rubin Observatory would kind of be the lookout, trying to find these objects. And if Comet Interceptor were to be actually developed and launched, it would be out there in space near the Earth, but just sitting kind of waiting for kind of in hibernation almost, just waiting. And as soon as Rubin found one of these interesting objects that was close enough to us and with a small enough delta V, so energy boost that the spacecraft would need to be able to go get to it, then the Comet Interceptor spacecraft would go do one of these close flybys of the comet, trying to take pictures really up close and personally, gathering as much information as possible about that comet as it then went through the solar system. Even if it doesn't look like a comet, if it's something like Oumuamua, you could still do the same type of thing. So that is one of the things that we as astronomers would love to see. And there are already kind of programs like this that have been in the works that we're hoping will be able to move forward to be able to do this very kind of thing. Because that's really how we would get the most information, not just in our current capabilities with Rubin or JWST, as well as finding more of these, is that if we could have a spacecraft that could go really, really close to the object and take all kinds of images and measurements, then we would really be able to understand the details about what that particular object is.
Is there any like personal questions, like burning questions you have that you hope that we haven't talked about already? That you're what's most exciting to you, having worked on this project for so long, having studied this, studied this, researched this. What are the questions you hope to answer? What are the things that excite you the most of Rubin coming online over the next year?
So, one of the things that I enjoy getting to study the most in my work are objects in the solar system, mostly asteroids, that get into places or orientations or orbits within the solar system that are really unusual and surprising, that really make you ask, how in the world did that get there? How would it be possible for that asteroid to be in that part of the solar system doing that kind of thing? And so these really rare, unusual type of objects, I'm really excited for Rubin to be able to find more of these type of objects. So, for example, um, we uh, we know of one asteroid in the solar system that's actually orbiting the sun backwards. So it's going opposite the direction of pretty much everything else in the solar system.
I didn't realize you typically things only orbit in one direction.
Right.
Okay.
Right. Pretty much everything, because of how these solar systems form and they kind of make this flat disk,
Someone
everything
needs to have a talking
orbiting.
to that asteroid. Someone needs to give a good talk to that asteroid. Let them get them with the program.
Yeah. Yeah. So that's one of these things that really make you go, how is this going backwards? How did it get there? And so a lot of my work, in addition to observational parts of astronomy, is more of the like theory and simulation part of astronomy, of then trying to understand where these objects came from. And so I actually discovered many years ago a way for asteroids to be able to get onto these backward type of orbits. Um, but we still don't know a lot of the details about how this works. And so I'm excited for Rubin to find more of these objects so that we can study them in detail and better understand how they got there. And even many more different types of really weird, kind of strange, unusual type of objects around the solar system, in addition to just having so much more data to be able to understand not just how some of the weird things about how the solar system works now, of things that work in ways that we don't necessarily expect, that I would love to find answers to, but also just peering back farther in time and being able to understand more about how our solar system formed, um, and kind of how it's changed over time. And I guess the other thing is I want to know if there's another planet in the outer solar system. I want to know if this theoretical Planet 9 or Planet X that you maybe have heard about.
No, I like it. Is it? This is a hypothesis. So something further out that's beyond Pluto. That's kind of another planet. Why do we think there's something like that that exists?
Yeah, so there's so it kind of dates back. There's kind of a long story that leads up to things. Partly it started with Pluto no longer being called a planet. Maybe you've heard that Pluto got demoted to
Yeah.
dwarf planet
And
status.
where do you stand on this very contentious issue of is Pluto a planet?
I I think it's helpful to have a clear definition of what a planet should be. Um, but and So part of the reason for not having Pluto be a planet anymore is that we found many more objects in the outer solar system that are just as big as Pluto, also very similar in size, and that are kind of sitting out there in this big Kuiper belt. And so if there's all of these other objects like Pluto as well, you either need to start memorizing many, many more objects as being planets in our solar system, or it then only makes sense that maybe we shouldn't actually call Pluto a planet anymore because it is very similar to these other category of objects that aren't quite the same as the rest of the planets in the solar system, but are still uh, bigger and kind of in their own category to the rest of the asteroids and comets that we have. So um, I kind of understand, but at the same time, it's kind of sad not calling Pluto a planet anymore. I understand all of the people that were very mad about this when it happened, that people want Pluto, which is often their favorite planet, to stay a planet. Um, but so part of the evidence with demoting Pluto is that we found all of these other big objects in the outer solar system, and we've been slowly finding more and more of these objects that are on orbits as they go around the sun that are, when we first started finding these things, they all seemed to have their orbits kind of, again, clumped in one part of the solar system. So rather than having them be kind of uniformly distributed around the entire disk at any different angle around the sun on these kind of long stretched out orbits, they all kind of seem to be squished together. And so this led some astronomers to think, well, if these objects are all in only one part of the solar system and not elsewhere, maybe that means that there's something else that's really massive in the outer solar system that actually is pulling on these objects, keeping them this kind of clumped type of orientation. And so that is what led to this hypothesis that maybe there is this other massive planet that could be anywhere from like 10 to 15 times more massive than the Earth. And I think the current estimate is that it's something like 700 times farther away from us than the sun. So it's really far out there, way farther than Pluto or the rest of these objects. And so over time, astronomers have been trying to find more of these. They're called extreme Kuiper belt objects because they're on these really long, stretched out orbits. They've been trying to find more of these to see if when we find more, they all continue to appear clumped in one part of the solar system, or if they're more kind of evenly distributed around the solar system. And so as we've been finding more of these things, the evidence has kind of been waning a little bit for the existence of this other planet because there are more of these things that are a bit more kind of evenly distributed around the solar system. And so they don't quite appear as clumped as when we first started finding the first few of these things. And so it's still kind of unclear whether there's this other planet in the outer solar system or not. But Rubin Observatory is going to bring us really much closer to trying to figure out whether there is, because it's going to find so many more things in the outer solar system. It should find many more of these extreme Kuiper belt objects, and it will then be able to tell us whether this clumping is actually real or if it was just some kind of effect of how we happen to find these first few objects or not. And there's a chance that we may even be able to actually find this other planet directly. We might actually be able to find it in some of our images. It's hard to say if we might or not because the range for how massive it would be, so how big it is or how close it is to us, is a little bit of a big range. So it's kind of uncertain whether it's close enough or big enough for us to actually be able to see it with Rubin. But if it's out there, the way that I think the most popular theory for what it should look like right now and where it should be, I think that the Rubin Observatory should be able to see it. So if it exists the way that people think it might, we should be able to see it. And so if we don't, maybe that means it doesn't exist.
Okay, well, that's amazing. And so the hypothesis is, and are people calling this Planet X? What did you?
Some people call it Planet X. I think more recently it's been called Planet 9, which has the people who are in support of Pluto still being a planet kind of upset because Pluto is the ninth planet if you still count it as a planet. So then
So basically, if you demote Pluto, this could be Planet Nine,
yes, yes.
the real Planet Nine. Okay, well, wow, this is amazing. I could keep on going. This has been a fascinating conversation. And you left us with a super interesting topic that I really want to go deeper into, but maybe in another time we could do that. Thank you so much for this comprehensive exploration of the Vera C Rubin Observatory, its mission, the things we hope to find near us and far from us, how it ties into discoveries that we might be able to make in physics and energy. So I'm super excited, and I really appreciate the time you spent with us. Any other last comments or thoughts or things you want to share with our audience?
Well, first of all, thank you so much for having me. This has been a really fun, enjoyable conversation. I think just as final thoughts, we as the astronomy community are just incredibly excited for all of the discovery that we are going to be unlocking very soon with the Rubin Observatory. And we are going to be trying to make sure a part of our mission is being able to make sure that we share all of those discoveries with the world. We want to make sure that this isn't just kept as something that scientists get to know about and be excited about. We want to make sure that everybody has a chance to be able to share in all of that excitement and discovery with us. So we will be making sure that we have lots of media announcements and press information when we find these new things to be able to share with everybody. And we invite people to follow us on social media or go to rubinobservatory.org. We have so much information already in there about the observatory and our goals, and we're really excited to be able to find out so many things about the universe for ourselves, but also make sure that everybody else can share in that exciting discovery as well.
Fantastic. Looking forward to this as you are. Thank you so much, Dr. Greenstreet, for joining us.
Thank you.